Now, after talking about the physics quantities in kinematics, now we're going to talk about their relationship. Relation. A few relation that we're interested in, includes position time, velocity time, acceleration time, and velocity position. Okay, so we kind of briefly talk about why we want to study this relationship before, and later on when you apply this relation in some problems, you can see they're actually pretty powerful and useful. Unfortunately, we do not have a universal equations or universal laws that tell you, to predict all kind of motion in the world. We kind of have to do it case by case. For example, the motion, like a circular motion and the free fall motion, they're completely different things. So you don't have a one equation or one graph which can describe two things together. So that's why we need to do, when we talk about different cases, we just need to focus on that motion and develop the relationship for that case. This week, we're going to just focus on three simple cases. Constant position, constant velocity, and the constant accelerations. We will also talk about random cases, but the random cases will be just like a combination of the first three cases. So that will be, if you know how to do the first three cases, then you're good. So let's take a look at the case one. To study the relationship in a motion, we can use a few different ways to study it. So the first way is we can describe the relation by words. We can also describe this motion by graphing. And lastly, in physics, we also love describe the motion by equations, by math. Okay, we like to cook up one equations and you put in the time, then I would immediately tell you the position. Okay. So I'm gonna show you how to do three of them in this case. So say, now imagine that there's a student called Jake, and Jake is standing at this position, x0. Okay, so x0 could be like 2 meters, 3 meters, whatever. It's just, it just means the position. So Jake is standing there and he's not moving at all. So his motion is, so this motion we call it constant position. It means that Jake is standing somewhere and not moving. The position is a constant. So when we want to describe it by word, the position versus time relationship would be position of Jake is x0 all the time. That's it. So it seems pretty straightforward. Everyone can do it. And how would you describe the velocity versus time of Jake? Well, the velocity of Jake is 0 all the time. And how about acceleration time? Similarly, it would be acceleration of Jake is 0 all the time. So you can see all these sentences, they will tell you the position, the velocity, and the acceleration of Jake at any time. So that's it. We can describe these cases by these sentences. Okay. So now let's try to describe the motion of Jake by, let's say, graphing. How would you do that? So first, let's try out about the position and time. Okay, so Jake is standing here, right? And you know that Jake is not moving. So if at time equals 0, Jake is standing at x0, then he's gonna just stand at x0 all the time. He will not move. You will see a constant function. And how about the position? Sorry, how about the velocity? Well, in the velocity, what's the velocity of Jake? It's 0, right? It's not moving, so it will be 0 all the time. Okay. How about the acceleration? acceleration of Jake will be, again, it will be 0 all the time. Because Jake is not moving at all, and he's not accelerating to anywhere. So you see, this is how we can describe the motion by graphing. So when you see this graphing, you can predict the motion. You see these graphs, then you can predict the motion of Jake. Okay. Right. Clear the drawing. So this is our answer. And next, let's try to describe the this motion by math. Like, how would you do it? For the position and time, we know that Jake is not moving at all, right? So it's basically staying at this position all the time. So if I want to have an equation that will tell me where Jake is, that equation is nothing but x naught. Because no matter what time I put in, you can see this x has no dependence on time. So no matter what time I put in, the position will always be x naught. It will always be this constant x naught. So similarly, what's a VT relationship? What's a velocity? How does a velocity depend on time? Well, it doesn't depend on time at all because it's not moving, right? Velocity is 0 all the time. It doesn't matter what time it is, it's just always 0. Similarly, the relationship between acceleration and time is just a equals to 0. So these three equations will faithfully describe the motion of Jake. If you just tell people, oh, there is a person going with this, its motion looks like this, then other people will immediately know you're talking about this scenario. So this is three different ways to describe the motion of something. It's a very simple examples. Later on, you will probably see more complicated example, but it's very important that you can, you know how to convert from one representation to another one. So for example, if I give you the graph, can you predict the math? If I give you the math, can you tell me what's actually happening? So that's something that we will practice a lot. That's the answer. Okay, now let's come to the case 2, constant velocity. Constant velocity means that something is moving at a constant speed and in the same direction. How would you describe the position time in terms of sentences? I guess I will say, well, Jake starts from position x naught at time equals to 0. And the position increases with the rate of v naught, like meters per second. Yeah, so I guess that's all what I can say, right? Like the position is increasing with the rate of the speed. And what would you say about the velocity versus time? Well, it's a constant velocity. So velocity will be the same all the time, which is v naught. How about the acceleration versus time? Acceleration is going to be 0 because it's not accelerating. It's a constant speed all the time. So you can see, even in this constant velocity, this kind of simple motion, using sentences and words to describe that motion is not very efficient. But we can still do this efficiently with the graphing and the math. So let's start from some simple relationship. Why don't we start from VT plot? What's the VT plot is gonna be like a constant because we know this is constant velocity. Velocity is just always v naught. It's not changing at any time. So what's next? How about acceleration? What's the AT plot gonna look like? It's gonna be like this, right? Because there's no acceleration, Jake is not accelerating anywhere. So its acceleration is 0. How about position? Well, we know Jake is definitely increases in position as the time increases because it's going to the right. But is Jake is the position going like this, or this, or this? All of them are possible, right? So let's think more about it. Which one makes more sense? So to help us think about it, I'm gonna put in some numbers to help me think. I'm gonna say Jake starts from 1 meter and is moving at 2 meters per second. So now I know at time equals to 0, Jake would be at 1 meter. And after 1 second, Jake will be at 2 meters. And why is that? Because the speed is 2 meters per second, so that means Jake will move 2 meters every second. So that's why, oh, sorry, it would be 3. So that's why after 1 second, Jake will be 2 meters away from the reference point. And 2 meters away from the reference point, so it makes the final position to be 3 meters. So Jake will be at 3 meters after 1 second. And similarly, after 2 seconds, where is Jake? After 2 seconds, Jake will move another 2 meters away, so that brings him to the position of 5 meters. So Jake will be at 5 meters. Now let's connect all the dots together, and then we will get a plot like this. Okay. You see, this is a linear plot. And this linear plot makes sense because Jake its position is increasing at a constant rate. That's the meaning of, which is exactly the meaning of speed, right? Increasing at a constant rate. So this is what the plot look like for constant velocity, linear. For position time, it could be linear like this or linear like this, because Jake might be, moving to the left. So, but basically it has to be a linear line. And then, constant for VT and AT. Now let's come back to think about how to describe this motion by math. Again, let's start from the easy one. So let's see. What's the acceleration at time t? Well, the acceleration at time t will be 0 because there is no acceleration. How about what's the velocity at time t? The velocity will be v0 because the velocity is not changing. So now you can see we immediately know the relationship for these two cases. And how about position? Where is Jake after some certain amount of time? Where's Jake? All right. Now we need to give it a bit more thoughts. So remember we're saying what's the meaning of velocity? We know here velocity is a constant, and we know that velocity is nothing but the change of position over the time, right? Over the change in time. So if I want to know where Jake is, we want to know its final position, we can manipulate this definition. So I'm gonna move t to the other side. So on the right-hand side, I will have x minus x naught. So I will get this equals to vt. And then I will add x naught on both sides to move x naught to the right. Then this will tell me where Jake is at time t. And this equation actually makes a lot of sense. It's very consistent with what we were saying. So let me give you some numbers to help you digest this equation. So you see, remember we were saying that, so for example, Jake starts from 1 meter and it's moving at 2 meters per second. And we said that after 2 seconds, Jake will move all the way to 5 meters, right? This is the number that we cook up and when we try to draw the picture. Okay, so let's see. So where is Jake? We know that Jake after, if t is 2 seconds, if this t is 2 seconds, where is Jake? We know Jake after 2 seconds, it will move away from the original point by 4 meters. And we get that because we use the speed 2 meters per second times 2 seconds, which is 4 meters. So we know Jake will move away from original point by 4 meters. If Jake initially starts from 1 meter, then he will definitely end up at 5 meters, right? And this is exactly what this equation is talking about. Where's Jake? Jake is away, is starting from its original point, 1 meter, and then he moves 2 meters per second times 2 seconds equals 4, and he moves 4 meters away. He moves 4 meters away. So he ends up at the 5 meters, at the position of 5 meters. Okay. So now you can definitely try to think about it by yourself. If you need it, just put in some numbers to help you to think about the meaning of constant velocity. So that's it, and that's a relationship of that's a math description of this plot. The third example we're going to talk about is constant acceleration. So constant acceleration means Jake is here, and then he's moving faster and faster and faster. He's accelerating with a constant acceleration. So every second, he will move faster than the previous second. So that's the meaning of constant acceleration. And now you can see it becomes really hard if we want to describe their relationship by words. Okay? Positions will keep increasing and increasing more at higher rate. Like, it's not that easy. But if we describe it by math and graphing, it will be still very concise and elegant. Let's try the graphing first. So let's just start from AT plot. We know acceleration is constant, so it should be flat for AT plot. How about VT plot? Well, now you probably know it's gonna be a linear line, right? Because Jake will start from some velocity, and then the velocity will increase at a constant rate, will increase every second. The velocity will increase at a constant rate because it's a constant acceleration. Okay. You see, it's a linear. It's kind of like the same with the previous case. So it's just now it's constant acceleration. How about XT plot? All right. Again, whenever you want to draw a picture but you don't know how to start, just pick a few points to start with. So I'm gonna say I know that in the beginning, Jake was in the position of X0. And what happened after 1 second? Well, after 1 second, Jake is moving to the right, so it will be, say, somewhere here. How about another second? So after 1 more second, we know Jake will be still moving to the right, but Jake is moving faster, right? It is moving, the speed here is higher than this. So Jake is moving faster than before. So during this 1 second, during like from 1 to 2 seconds, Jake is gonna move further than this. It's gonna move more than this. Similarly, after another second, Jake will be moving even faster. So so from 2 to 3 seconds, it's gonna move a lot more, maybe somewhere here. If we connect all the dots together, it's gonna be something like this. It's gonna be something like this. So this is a quadratic. You can see Jake is not moving so much in the first second, but it's moving more and more and more and faster. Basically, the slope here represents the velocity at that time. So that's what the graph will look like. It will be linear for VT and quadratic for XT. Now we can start to build the mathematical functions based on this. Mathematically, we know that, well, acceleration is just, it's constant, so it's a naught all the time. How about velocity? We can pull the same trick, right? So we know here, if we want to know the velocity at a specific time, then we can start from, the definition of acceleration. Remember that we said the average acceleration is the change in velocity over the change of time. And the acceleration, average acceleration here is just a naught because acceleration is the same. It's not changing. So average acceleration during this time period is just a naught. And the velocity definitely changes because of acceleration. So it looks like this and over the time t. Now, because I want to find what's v, so I'm going to move this t over to the right, to the left, and then rearrange my equation. All right, I'm almost there. Okay, so that's it. This is an equation for velocity. V equals to V naught plus A naught t. If you tell me the initial velocity and initial acceleration and tell me what time you want to know the velocity, just plug in all the number, then the velocity will pop out. So it's a very elegant, like one-line equation describing the motion. And this is also the general equation for constant acceleration. And how about the position? So for position, we can also use the same trick to derive the xt plot, and I will do this in another video because it's a little bit longer. But basically, after you did all the math, you will get the xt relation looks like this. So this is the xt relation, and this is the vt relation. This is at relation. So this is the equation that you will need when you encounter a constant acceleration problem. Okay, so that's it. Sometimes you may encounter more random cases. For example, maybe you have someone moving in this way. Then what's a VT plot looks like? What's the AT plot looks like? For questions like this, you can always, cut it into little pieces. And you know what is this? This is a constant velocity, right? This is constant velocity. This is constant acceleration. Then you can piece them together here based on what you know. And same for here. So we will do some practice and then you will get a better feeling about this.